I think this is going to flip. I think that the seismic activity will slow down. And I think at some point we're going to go back to a negative phase of the AMO. And I think the temperatures are going to cool down and the whole system's going to calm down. And a lot of people are going to walk away with a lot of egg on their face.
My guest today is Arthur Viterito.
I'm a retired professor of physical geography. Spent nearly 40 years in the academic warrior world. And I have a specialty in physical geography with interests in climatology and geographic information systems. And I have been working on this whole issue of what's been causing the recent warming now since about 2007, since the time that Al Gore's documentary came out on this, The Inconvenient Truth. I have been inconveniently trying to find the real truth in all of this, and have come up with what I referred to as the geothermal paradox, a hypothesis that most people have overlooked and or ignored or have criticized in some very weird ways. So I will hopefully be able to present this to you today because I believe it's this geothermal paradox that's driving the most recent warming that we've seen since the mid-90s. Now, until recently, there's been very little research on the impact of geothermal heat on global temperatures. The reason there's been so little interest in it is because we really don't have a large amount of geothermal heat relative to what the sun puts out. We're talking very, very small amounts relative to the solar output. And most people have been focused on that, or they, of course, have been focused on the role of carbon dioxide as a greenhouse gas causing the most recent warming. So we're going to take a look at this. And as we can see here, most geothermal heat for the planet is found in the middle of the world's oceans, in what are called the mid-ocean spreading zones, also called the mid-ocean ridge system. And we see that the vast majority of the mid-ocean heat is found here in the East Pacific, in an area referred to as the East Pacific Rise, down here in what is referred to as the Mid-Atlantic Ridge. And we have a number of ridges and rise complexes out here in the Indian and Southern Oceans. In fact, the Mid-Atlantic Ridge has gotten a lot of attention recently because there's been a tremendous amount of volcanic activity in Iceland. They've had to evacuate whole towns. And what it really is it's the northern edge of the Mid-Atlantic Ridge that's been very active lately, also known as the Recanus Ridge as we get off the coast. So this area has been very active recently. And I've looked at this and said, okay, how is that activity varied through time and space? Because obviously it has. And here we see a map of the 60,000 kilometer long system of underwater volcanic mountains, and what are referred to as hydrothermal vents. And this is called the mid-ocean ridge system. We again see this is very, very well mapped out. They have done the mapping through sonar and LiDAR technologies. We have a pretty good understanding of the macro geography, so to speak, of the ocean floors. Now, the mid-ocean ridge system is an area also referred to as a rift zone. It's an area where we have what is referred to as normal faulting. It's an area where the lithosphere, the crust, is being pulled apart. And we can see here that as the crust is being pulled apart, new oceanic crust is being formed along what is called the spreading zone centers. So along this rift zone, we tend to have lots and lots of volcanic and what's called hydrothermal activity. Hot magma reaches up, percolates to the surface, heats the water sitting directly above it, and this we can see causes some serious changes or significant changes to what goes on in terms of the deep ocean circulation. If we focus in on this, we can see here a cross-sectional view of this. We have what are called black smokers and white smokers. The black smokers can reach temperatures of 700 degrees Fahrenheit, white smokers 300 to 400 degrees Fahrenheit. And of course, we have this massive system of vents and fissures where we have lots of water percolating through the system, exchanging heat with the mantle underneath it. Now, here's what I call this the geothermal paradox, because The average geothermal flux at the surface is just 1/10 of a watt per square meter. And people say, well, this isn't enough heat to really make a difference in terms of the global climate. But nonetheless, we know that geothermal heat does a tremendous amount of work. It's able to move the Pacific plate 4 inches per year. It widens the Atlantic basin by 1 inch per year. It can eject enough ash to cool the globe many degrees Celsius, Krakatoa, Tambora. And it can eject ash and water 35 miles into the atmosphere, as it did in the Tonga eruption in early 2022. So we'll say, okay, we have the system of underwater volcanic vents and hydrothermal vents and volcanoes. What's going on here? We know that we have no or very few direct measurements of this. Specialty research has done some research on this. Things like Scripps and Columbia Laurent Doherty have done some work on this. But we have to use what are known as proxy indicators in this case. So in this case, I will read you the quote. This is citing from an article in Nature. Seafloor hydrothermal systems are known to respond to seismic and magmatic activity along mid-ocean ridges, often resulting in locally positive changes in hydrothermal discharge rate, temperature, and microbial activity. Corresponding regional effects have also been observed. So the more seismic activity we have in these mid-ocean ridge systems, the more magma and the more heat we know is being emitted from these systems. Now, as I said, we don't have a lot of data on the direct heat flow, but we do have a global system of seismographs that has very accurately and very meticulously plotted the amount of seismic activity that we find on the ocean floor in these mid-ocean systems. So we're going to use that as our proxy indicator, knowing that high seismic activity in the mid-ocean system also correlates with very, very high hydrothermal heat coming up. We know that these hydrothermal systems cover large areas of the mid-ocean ridges and their flanks. And we know that most of the hydrothermal heat loss occurs on the flanks of these ridges, and the temperatures are lower, and the seawater flux is correspondingly larger. The estimated heat loss on the flanks is so large that upwelling or convective activity must occur over a large fraction of the seafloor less than 65 million years in age. And this is a very, very important point, because what it says is that the more hydrothermal activity you're going to have, the more convection you're going to have at the bottom of the ocean. And this is critically important because it affects what is referred to as the thermohaline circulation, also referred to as the meridional overturning circulation. It is the giant conveyor belt that moves heat and mass along the entire ocean system. And this is a game changer, because if we can cause greater convection on the ocean floor, we can change the intensity of this thermohaline circulation. The oceans contain 1,000 times as much heat as the atmosphere, and this in turn enables geothermal heating to enhance the ocean's ability to transfer heat. If you want an analog to this, it's sort of like a thermostat in an automobile cooling system. If that thermostat is open, then the water can freely circulate and you get a very even temperature distribution. And in fact, your car will never get up to what's called running temperature. But if you have choke points that, in the case of an automobile, if you close that thermostat, all of a sudden you now start to transfer heat in some very profound ways, i.e. your car gets up to running temperature and you can actually heat the interior of the car. So we see the same thing going on here. That is, the additional geothermal heating at the bottom, which is indicated by increased seismic activity at the bottom, can also affect the intensity at which this the thermohaline circulation moves through the system. And here we see this in 3 dimensions. We see that the surface currents are denoted here in red, and the bottom water currents are denoted here in blue. Now, what happens is that we have distinct areas of what's called upwelling and downwelling in the system. That is, here in the Arctic, we have what is called downwelling. That is, surface water moves up into the system through the North Atlantic and then downwells into the Atlantic bottom water. It then circulates through the system and it comes back up here in the Pacific. And also over here in the corner, the diagram isn't quite detailed enough, but we can see that there is some upwelling here around Antarctica. So what we have here are distinct areas of upwelling. As I said, Antarctica, just south of South America, and then downwelling of water moving downward over Iceland. And this is critically important because we have to sort of cite the literature on this, and this is where people tend to ignore things. Although the ocean is largely heated and thermally driven at the surface, several recent studies suggest that the ocean geothermal heating can also affect the ocean dynamic and heat budget. By applying spatially constant or variable heat flux in the ocean general circulation models forth with the present day climate, it is shown that ocean geothermal heating is a significant force that can weaken the stability of the water column, warm the bottom water, and strengthen this thermohaline circulation. So this conveyor belt doesn't move at a constant rate of speed. It can be sped up or it can be slowed down. And this has profound importance. Other studies say that the destabilizing geothermal heat flux tends to promote a more vigorous full depth overturning, having approximately 10% greater volume flux than with no bottom heating. And this is really important. If you can increase the rate at which the ocean overturns its water by 10%, you're going to have some significant impacts from this. Geothermal heating induces a substantial change in the deep circulation, which is larger than previously assumed. The numerical ocean model responds most strongly in the Indo-Pacific with an increase of meridional overturning of 1.8 spheredrupes. A spheredrupe is 1 million cubic meters of water per second. So we're talking rather large quantities of water here. For example, the global rivers produce about 1.5 spheredrupes. This roughly equals the total output of the oceans. So the overturning is enhanced or intensified by up to 25% due to the geothermal heating of the bottom. It is known that geothermal heat strongly intensifies. This is from a study in Journal of Geophysical Research. It is known that the geothermal heat strongly intensifies meridional overturning circulations. The Atlantic enhancement in the globally heated experiment is much weaker than ours. And this might be because of the difference of the magnitude of the geothermal heat flux. So we know that differences in the heat flux, which is going to reflect in the seismic activity, greatly impacts the rate at which the ocean overturns. And finally, another study here that appeared in Geophysical Research Letters says the abyssal warming around Antarctica is one of those prominent multi-decadal signals of change in the global ocean. Here we investigate its dynamic impacts on the Atlantic meridional overturning circulation, which we'll talk about later. This is a critically important component of the system. The simulation suggests that the ongoing warming of Antarctic bottom water, already affecting much of the southern hemisphere at a rate of up to 0.05 of a degree C per centigrade, has important implications for the large-scale meridional overturning circulation in the Atlantic Ocean. Okay? So we know that excess heating at the bottom affects what happens in the North Atlantic in terms of the surface movement of water and subsequently movement of water back down. So knowing this, if we start to put things together, we say, well, what has happened with these mid-ocean zones in terms of their seismic activity? Knowing that the greater seismic activity that we have is indicative of greater geothermal heating. This is well established in the literature. Nobody is arguing this. So what I've done here is I've taken the mid-ocean spreading zone seismic activity, which I call MOSIA, since 1977. And And I've culled this data from what's called the GCMT catalog. It's put out by Columbia University. It's a complete catalog of seismic events going back to 1977. And we notice that the amount of seismic activity had come up since late 70s and into the mid 80s, then actually flattened out and came down a bit. And then in 1995, we have an inflection point where the mid-ocean seismic activity trended back upward and has continued back upward since then. So 1995 is a critical inflection point in our system here. And that gives us a lot of clues that I will present to you in just a moment. Global temperatures from 1979 have first been reported from satellite data since 1979 through, I have this down through 2022. We haven't finished 2023 yet. And here we see a similar pattern. That is the University of Alabama, Huntsville temperature data plot for global temperatures is very similar to the data plot that we see for the seismic activity. There is one significant point in all this. If we look at the dates real carefully, our plot here starts in 1977, and our plot here starts in 1979. So the seismic activity, we plot back to 1977, the global temperatures back to 1979. This is the first year we had satellite data. This is as far back. Actually, this data set goes back to 1976, but we'll explain why we started with 77 in just a minute here. So we see the shape of the two curves is very similar, but there appears to be an offset by 2 years. So if we match the 1977 data for seismic activity with the 1979 global temperatures, and then go for 1978 seismic activity and match it up with 1980, in other words, if we factor in a 2-year lag, we end up with this composite curve. This composite curve shows global temperatures plotted against mid-ocean seismic activity with a 2-year lag. And this has an extremely, what we call goodness of fit. And in fact, it even has a goodness of fit that corresponds with all of the El Nino and La Nina episodes. And these are the spikes up and down that we see in the system. And we see that the match here is extremely good. We have a correlation coefficient of 0.74, which is extremely high. And the probability, this is a remarkable number, the probability that these two curves match up this well as a chance occurrence is something like 1/100 millionth of a percent. It's an incredibly small number. This has to be a meaningful correlation. And I hear this all the time. It's like, well, correlation isn't causation. I said, but when you have a goodness of fit that's this tight with that kind of a ridiculous probability value, you know something is going on. And I think it's incumbent upon the research disciplines involved in this to look at this. Well, I have. And another thing that jumps out here, and we're going to hopefully tie this all together by the end of the discussion. Hopefully people will be able to see this. If we look at the decadal temperature trends from December 1978 through December 2022, we see some interesting things. This, again, is from Roy Spencer's data at the University of Alabama at Huntsville. We see that we have, yes, quote unquote, global warming, but the vast majority of it occurs up in the North Polar region. This is referred to as the Arctic amplification, which we're going to spend some time with. We also see a secondary peak here in the Northern Hemisphere extratropics. And then as we move down past the Northern Hemisphere extratropics into the tropics, Southern Hemisphere extratropics, and then the South Pole, we see less and less warming. And this kind of the skewed distribution tells us something else has to be going on here, that there's a very uneven distribution in the way that the globe is warming. Now, if the global warming as a result of carbon dioxide, which is what the catastrophists are telling us, we would expect to see a much more even distribution of temperature. But here we see that the global temperature anomalies are very heavily skewed towards the North Polar region and the Northern Hemisphere exotropics. This is a remarkable chart here that people choose to ignore. So if we look at the thermohaline flow in more detail, we see that there are two very important, what I call choke points in the system. Excuse me. One is here in the Western Pacific, and the other is here in the North Atlantic/Arctic. That is, in the open Pacific, in the Central Pacific, there are no restrictions to the flow. But as we get here into the Western Pacific, we see that the thermohaline circulation runs into Australia, Malaysia, Indonesia. It hits the topographic barrier effectively. Then as it squeezes out through here into the Indian Ocean, again, no barriers, and then it wraps around. And then we see here that it runs into what I would call a cul-de-sac, the Arctic Basin, which is an enclosed basin. It has no place to go. But it does find a place to go. It goes downward. So these two choke points, I believe, are significant in our scheme of things. The next 12 slides are going to provide concrete evidence that starting in 1995, the intensified thermohaline circulation significantly impacted temperatures along with a host of other geophysical phenomena in the North Atlantic and the Arctic. So 1995, to scroll back here, you can see here is our inflection point when the seismic activity started to spike upward. And I wrote a paper on this called 1995, an important inflection point in recent geophysical history. First, we see that we have an abrupt shift in what's called the Atlantic multidecadal oscillator. And this changes, the oscillator changes in 1995. It flips from negative, meaning cooler North Atlantic temperatures, to warmer North Atlantic temperatures. This AMO index has been positive since, as we said, 1995. And this is not disputed. I mean, this is directly from, this is NOAA's data. And here we see anomalously high temperatures associated with that positive AMO. And again, we see anomalously high temperatures here in the North Atlantic and up into the Arctic. And we also see anomalously high temperatures here in the Pacific. The Southern Hemisphere is very unremarkable, which matches up very, very nicely with this. So obviously, there's been a change in the AMO, which we've documented, and nobody's commenting on this. They're saying, well, it's carbon dioxide. Okay. But Southern Hemisphere, no such problem. Now, an incredibly important study was done recently in 2020, and the rapid change in the AMO index is clearly reflected in an abrupt change in the phytoplankton populations in the Arctic. So here we see real-world evidence that backs up the temperature distribution. In other words, we see another geophysical system, in this case, the biosphere, has been impacted by this. So Oziel and I'll say that the Arctic marine biome, shrinking with increasing temperature and receding sea ice cover, is tightly connected to the lower latitudes through the North Atlantic. By flowing towards by flowing north through the European Arctic corridor, the main Arctic gateway where 80% of inflow and outflow takes place, the North Atlantic waters transport most of the ocean heat, but also nutrients and planktonic organisms towards the Arctic Ocean. Using satellite-derived altimetry, we reveal an increase up to twofold in North Atlantic current surface velocities over the last 24 years. The date of publication is 2020. Over the last 24 years, that takes us to 1996. 1 year past, we see the inflection point in 1995. We also see an abrupt increase starting in 1995. Here it is designated by this tall bar. And Atlantic hurricanes and what's called their accumulated energy. ACE is called the accumulated cyclonic energy for these systems. So when the AMO flips into a warm phase, we see a sudden jump in the intensity of hurricanes and in their frequency in the North Atlantic. Here we see a lull during the negative phase, during the cold phase, and here we see a jump up back here back in the 1950s and 60s, due again to the positive phase. We also saw, this is a study that was in Science Advances, we also saw the beginning of a decline in cloud cover over Greenland in 1995. This makes sense because higher temperatures will lead to a greater ability of the overlying atmosphere to hold more water vapor. So again, we see this sharp 1995 decrease in cloud cover. Global cloud cover also started to decline in 1995. And we see this is from the Satellite Application Facility. And we see here in 1995, here's our inflection point. We see it then starts to move downward. And now we have reduced cloud cover. We also see changes in freeze and breakup dates of ice in the Hudson Bay started again in 1995. Here is our 1995 marker. We see this jump up. We also saw rapid warming, what's called the North Atlantic subpolar gyre, commencing in 1995. Here, the demarcation is very, very strongly demarcated. And we see this jump up. And here's what the subpolar gyre looks like. It is actually an offshoot of the North Atlantic current. Commencing in 1995, there was an above change in fall and spring Arctic temperatures. Here's our 1995 breakpoint. This is from the Danish Meteorological Institute. And we see here, the breakpoint is very distinct. And the winter temperatures, they followed suit a little bit later. They were a bit of a laggard in this. Northern Hemisphere sea ice also started to decline in 1995. Here we see again our inflection point. Here we see things move upward in sea ice in the mid to late 80s. And then starting in 1995, here's our inflection point. Boom, it's downward since then. So we see that enhanced thermohaline flow is going to intensify the flow of water from the South Atlantic into the North Atlantic. If we head back here, we notice that right around the equator, this is where we start to see an increase in temperatures in the North Atlantic. If you intensify the thermohaline flow, keep in mind, if you follow the arrow, the thermohaline flow moves like this, southwestward through the Indian Ocean, rounds the Horn of Africa, and comes up here in the North Atlantic. If you intensify that flow, that means more heat and more mass, more water is being transported from the Southern Hemisphere, the subtropics and the tropics of the Southern Hemisphere, into the Northern Hemisphere. Here we see that subpolar gyre showing excessive amount of heating. And what you have now is more heat, more water being transported from the South Atlantic into the North Atlantic. Now, in the Pacific, we see something else going on. Enhanced thermohaline flow is going to cause more warm water to accumulate in the Western Pacific. What we call the physiographic and bathymetric features of that region restrict the flow of the equatorial current, creating a vast reservoir of warm water, and that's a driving force behind El Nino events. So as you can see here, water has to move through some very, very narrow choke points to get from the Pacific into the Indian Ocean. And here we see that north and south equatorial currents. We can see that they move here from the Eastern Pacific, make a beeline straight across the Pacific into the Western Pacific. What we get as a result of this, and this is well documented in the literature, is we get what is referred to as the Western Pacific warm pool. And this represents a massive store of heat that can redistribute heat across the entire Pacific basin when pressure and wind conditions switch from what we call a neutral phase to an El Nino phase. So what happens is that if you intensify the thermohaline flow, this Western Pacific warm pool can change. This is naturally occurring, but if you intensify the flow across the Pacific, this warm pool becomes more intense and it becomes larger. And a recent study showed this very, very nicely. This was this is by Kidwell et al. And we see here a comparison of the 1993 heat content of the Western Pacific warm pool, which is the top image, and the warm pool past that date in 2014. And if we look at this really carefully, we see that the temperature, the heat content is significantly higher than it is in 1993. And we see that the area of that warm pool has increased. An intensified flow in the Pacific will do that. If you're pushing more water across the Pacific, that warm pool will get bigger and it will get warmer. In addition to that, the thermocline, which represents the dividing line between warm water and cold water, also jumped abruptly in around 1995. We see here that the difference in the thermocline depth from 1982 to 2022 jumped up precisely right after the last El Nino, which was in 1998, the mega El Nino, which was in 1998. This is the last El Nino of the cooler period. We see this demarcation point. There is a 30-foot difference or a 10-meter difference in the thermocline depth, which is a lot. So here's a map from the 2015 Super El Nino, which shows the deepened and obviously warm Western Pacific warm pool. It spreads out over an immense area. If you increase the size of this warm pool and you kick off an El Nino, which is naturally occurring, you're going to increase the size of that El Nino. The warmer waters are going to cover a much larger area. It's the difference between taking a paintbrush and painting a small area of your wall and throwing a whole can of paint up against the wall. You just got more paint to work with. You're going to cover a larger area. Now, the strengthening of the Western Pacific warm pool has also warmed and strengthened what is referred to as the Kuroshio current and the Kuroshio extension. Here we see the Kuroshio current, which is off the east coast of Asia. It turns and then moves out into the Central Pacific to become what we call the Kuroshio extension. And here we see a detailed map of this. Here's your Indo-Pacific warm pool. And off of that, what is fed from that is the Kuroshio current, which is warm water. It's called the boundary current. It moves up the east coast of, western boundary edge of the Pacific Basin, is the east coast of Asia. And then the Kuroshio extension, which moves out into the middle of the Pacific. So, as reported in a study done by Adrian et al., Adrian Lamb, we see that the warmth stems from the surface waters that collect in the Western Pacific Ocean during the equator, called the Western Pacific Warm Pool. The Kuroshio current takes these waters north past the Japanese coast and then eastward at 36 degrees north latitude, where it joins the open Pacific. At this point, it becomes the Kuroshio current extension. Today, these currents are warming 2 to 3 times faster than other areas of the ocean. Ocean model studies and observational data show the Kuroshio current is shifting northward and increasing its transport capacity. Again, an enhanced thermohaline flow will do exactly that. As we can see, the Western Pacific warm pool has increased in size, in depth, and in its heat content. And as a result, this has impacted the Kuroshio current and the Kuroshio extension. And here we can see this. This was from April. Here we can see the warmer waters of the Kuroshio current and its extension out into the Central Pacific. Here we see the beginnings of the current El Nino, and here we see the warming of the Kuroshio current. Here we also see the subpolar gyre. So, if we take this up to a recent snapshot, this is taken from August 18th, we can see all of the things that we've highlighted in this talk are expressed in the global sea surface temperatures. So this is the NOAA map of sea surface temperature anomalies. Of course, the red areas indicate warmer than normal sea surface temperatures. We see here that the subpolar gyre has heated up. We see here that the Arctic Ocean has gotten much, much warmer. By the way, the term for this is called the Arctic amplification. And it's, again, well documented in the literature that this process known as Atlantification, that is the incursion of Atlantic waters, has caused this Arctic amplification. So here we see very warm waters in the Arctic. The subpolar gyre has definitely heated up. We see the heating up of the Kuroshio current and the Kuroshio extension, and finally an enhanced El Nino. So this Western Pacific warm pool, once you dissipate it, that excess heat and that greater volume of water is going to express itself in a warmened Kuroshio and a warmer El Nino. So, in summary, trying to figure out why CO2 is causing things to warm. We can see that the models do a terrible job with that. We really should be looking at this. And this is a sort of a unifying hypothesis as to what's going on here. And we've hit all the main points in our discussion here. That is, greater mid-ocean geothermal flux driven by increased mid-ocean seismic activity. We're connecting a lot of dots here, but they all do connect up. This intensifies the thermohaline circulation. Now, when you intensify the thermohaline circulation, those two choke points, the Arctic and the Western Pacific warm pool, react in somewhat predictable ways. If we look at the Pacific Basin, we see that increased oceanic heat transport into the Western Pacific then amplifies our El Ninos and our Kuroshio current, which gives us increased Pacific tropical and extratropical temperatures. In the Atlantic sector, increased oceanic heat transport into the North Atlantic and the Arctic gives us less cloud, lower ice, and that feeds back into the system. When you have less cloud cover and lower ice, you have less reflectivity in the Arctic, and that increases our North Atlantic temperatures. And this sets up a positive feedback loop in the Arctic, where it's going to keep enhancing the Arctic temperatures. So the Arctic amplification is very well accounted for in this model, as is the Kuroshio warming and the amplified El Ninos. This I've got a slightly more slightly cleaner version of this, and this paper is in review right now. I've got a paper coming out on this. So, what are the critics saying about this? I've gotten all kinds of weird criticisms from this. Most of it's been informal. Third party, I've heard through other people that they don't like this. So, for example, let me just cite one, and then we'll go through this laundry list here. One researcher said to me, a prominent researcher said, "I don't see that 1995 inflection point you're talking about. I don't see things changing in 1995." And I went, "Okay, somebody needs a better eye plan." But the first argument that's made is that there's not enough heat escaping to the surface to directly warm the overlying ocean and atmosphere to an appreciable degree. And the high correlation between mid-ocean seismic activity and global temperatures does not signify causality, as spurious results can arise if confounding variables are omitted from the experimental design. All right, this is grad school 101 experimental design stuff that's being thrown out here. We could easily refute these arguments in the following way. Although there is not enough heat to directly warm the atmosphere, we have modeling evidence showing that oceanic geothermal heat intensifies the thermohaline circulation. That intensified flow acts as a heat pump to distribute an increased amount of oceanic heat to two major heat sinks, the North Atlantic and the Arctic, and the Western Pacific. We've documented this. We have irrefutable empirical evidence to corroborate the modeling results. We've seen the Kuroshio warming. We've seen the warming of the Kuroshio extension. We've seen the North Atlantic warm. The entire chain of environmental changes, i.e. higher global temperatures, reduced ice and snow, enhanced El Nino events, is anteceded by the change in mid-ocean seismic activity. This is referred to as what we call Granger causality, and it strongly infers that a cause, i.e. one change occurs first, i.e. the change in thermal haline intensity, drives a time-dependent set of other variables, other perturbations occur afterwards. So this is an interesting epistemological construct. So ultimately, understanding the Earth's climate is a classic epistemological problem. Okay, it's the old, elephant. If you take a bunch of people only seeing one piece of the elephant, they describe an elephant as a different thing. It's a thing, it's a tree, it's a wall, but nobody's seeing the big picture. This takes a look at the big picture. And one of the problems I'm having, of course, in trying to get people to embrace this, is you talk to the atmospheric scientists that just want to talk to the atmosphere. You talk to the geologists and they say, well, there's just not enough heat down there. You talk to the astrophysics guy and say, well, the solar variability is not playing along with this. And everybody's playing to their own specialty. As I've always said, if you were to go see a cardiologist with a broken finger, they'd find a heart problem for you. I mean, this is how the sciences work these days. Nobody's doing this sort of integrative work. So we're just now beginning to grasp the complexities of the climate system. I mean, the drifting of plates over very vast stretches of time, of course, has a huge impact. The distribution of land, water. This effectively then sets up the system of currents on the planet. Sunspots, solar intensity radiation, we know that varies. Subaerial eruptions, of course, can cool the planet. We know the Krakatoa eruption, for example, we ended up with a year without a summer. Underwater, changes in thermal haline, and of course the Milankovitch cycles, that is changes in Earth's orbit. We know that all of these things impact climate, and I think what we need to do is come up with comprehensive models as opposed to just looking at one variable. In the case of the catastrophists, they're saying the only thing that's really causing this is CO2. And CO2 is a very weak greenhouse gas, and the human contribution to the entire greenhouse gas at best, is less than 1%. And they're saying this is the control knob, and yet they're ignoring all this other stuff, which just makes me crazy. So to quote one of my science heroes, Alfred Wegener, he says, "Scientists still do not appear to understand sufficiently that all Earth sciences must contribute evidence towards unveiling the state of our planet. It is only by combing the information furnished by all the Earth sciences that we can hope to determine truth here." If you talk to atmospheric scientists, they don't know anything about the oceanographic literature. They know very little about it. Again, if you talk to the astrophysicists, they don't know anything about submarine geology. And I think this is a fundamental error in the way we approach this problem. We need to sit down and look at all of the system's components. We need to look at the geothermal component. We need to look at changes in solar radiation, changes in cloud cover, et cetera, and to understand the feedbacks. Excuse me. We're having a high pollen day down here today. And of course, now we see that there's all sorts of nasty things happening in this area. The sign says it all. So, all scientists agree when you censor the ones who don't. We're seeing a tremendous amount of censorship in the climate sciences. My initial paper on this, which I published back in 2016, was rejected by 9 journals. And some journals wouldn't even review it. As one journal wrote back to me, a very prominent journal said, "Oh, well, this is kind of interesting, but don't you know that carbon dioxide is what's causing the globe to warm?" I'm going, don't. Fill me in on that one, please. I'm sorry I came up with a different idea. But we're seeing a tremendous amount of censorship. The peer review process, I think, is horribly broken. I think it's become horribly corrupted. I don't call it peer review anymore. I call it steer review. that these editorial boards just steer research into a certain, a fixed funnel or a paradigm that has an agenda attached to it. And this is really sad. The system is very broken. There's a lot of money, a lot of power, and a lot of influence tied into the peer review process, and that needs to be taken out of the system. We need to get back to a much more objective system of evaluating research. And of course, the Peanuts cartoon that trust the science is the most anti-science statement ever. Questioning science is how you do science. Questioning the science is the science. And we're finding that this sort of thought has been squelched tremendously. And it's very upsetting. And I don't know where we go with this. We just have to keep putting it out there, and hopefully at some point somebody's going to get wise to it and say, this is what we have to do. Some of the criticisms I've gotten on this are just ridiculous. I mean, I've heard some of the most absurd things by fairly reputable people in the field, and I just have to laugh it off. And thank you. This was all I have for the prepared presentation.
Do you have any ideas or predictions about what's going to happen in the next 40 years or between now and 2100?
So I think that there is a cyclical, we know of the 60-year cycle that does operate. And I believe it's tied to seismic activity.
Do you have thoughts on what is causing that 60-year cycle to happen every 60 years?
I think I'd get a Nobel Prize if I had that one figured out. It's very hard to figure out. We know that there are periods of general quiescence in the system. All I'm trying to do right now is just find some indicators. I'm just trying to find the sort of the keys to the kingdom over here. What is telling us what's going on? I'm looking for a drop in the seismic signal. If the seismic signal starts to drop, then we can start to make some predictions. And the seismic signal has not dropped. It's remained consistently high since. Actually, it's been very high since about 2000, 2001. So I'm looking for that. If I'm right and that seismic signal does come through, then we can start making predictions, knowing that there's a 2-year lead time in all this. So I'm hopeful, but hopeful is a lot different from being knowledgeable.
If there is a 60-year cycle and it flips every 60 years, what's the starting? Is it 1995, 60 years from that, or where do we start?
Yeah, you completely cycle through, because don't forget, we had a cooling period back in the 60s and 70s. We had warming back in the 40s and 50s. And it's 30 years of warming, 30 years of cooling. So we're right about at the 30 years of warming. If it started in 95, we're now coming into 2024. That marks the 30-year, or just about the 30-year point in it. And I'm looking for, and there's a colleague out there who keeps saying, I want the monthly stuff. I want to see when this thing's going to flip. I said, well, I don't know if it's going to flip, but if it does, it might be 35-year cycle this year for all we know. But if it's going to start to flip, it should start to do so relatively soon, if I'm right.
Okay. Is there anybody else's work that you really read up on and think that it's very good stuff? Anything you want to point out here?
I like the work that Willie Soon has done. Willie's done some very, very good work on solar cycles and total solar irradiance. I think I'd love to do some collaborative work with Willie, because what happened is we had TSI, total solar irradiance, kept going up, and then it decoupled around 1970. TSI decoupled from global temperatures about 1970. And I believe, in other words, TSI flattened out, and then it eventually started to go down. And now they're talking about it's going towards a grand solar minimum. But I think the geothermal has picked up the slack, so to speak. So I'd like to see some collaborative stuff if we could possibly build a database looking at both seismic and the TSI data going back further.
All right. Any other points you'd like to make before we wrap up?
Well, we're just going to keep trying here. It's a labor of love at this point, and I want to see if we can get anything, get some traction on this. I monitor this stuff on a very regular basis. As I said, I have another paper that's coming out hopefully soon, and I'm trying to figure out what are the what are the key indicators? And stuff's coming out every day. The biologists are doing good work on this with phytoplankton studies. There's good work being done in the oceanographic community on this. Another person who's done some interesting work is Professor Wis Yim from the University of Hong Kong. He has pointed to these underwater volcanic eruptions that become subaerial eruptions. They're very close to the surface. And he talks about these blobs, these hot spots that he's been finding out in the Pacific, and has tied them into different events of ocean warming. And Wis has done some good work in this. So hopefully I can collaborate with him, and maybe we can come up with some sort of comprehensive model of all this.
All right. How do you spell his name? I want to look up more information about him.
Wis, W-Y-S-S. His last name is Yim, Y-I-M. And he's an emeritus professor from the University of Hong Kong. I can send you his most recent presentation on this. I'll get that out to you today.
Okay. Yeah. And if there's a link to that, I might put that in the show notes too. Okay.
Right.
All right. Anything else?
No. I'm just going to keep trying. I appreciate you giving me an audience for this. I'd be interested in seeing what the feedback would be on some of this.
All right. We'll get it put up online. So thank you very much, Arthur Viterito. Talk to you next time.
Thank you, Tom.
All right. Goodbye.
Bye-bye.